Welcome to Tomorrow Unveiled.
And welcome back. This week on Tomorrow Unveiled, well, the pace of change. It's really forced us to look at a huge pivot point in global energy. It's quite something.
It really is. For years, the main story, and rightly so, has been what we call the green code. Solar, wind, these massive low-density sources you can roll out fast.
Yeah, their growth has been incredible. Revolutionary, really. Transforming grids everywhere.
But here's the thing our dedicated research team has really zeroed in on. The success of that green code, it's now creating this enormous, absolute need for something else entirely. Something denser, more reliable, something that just runs 24/7.
Exactly. And that mandatory need, that's what we're calling the hot core. So, this week's Tomorrow Unveiled is all about that convergence. We're talking advanced nuclear fission, early fusion steps, next-gen storage, all racing to meet this demand for power that's just always there, firm power.
Right. Our mission for Tomorrow Unveiled today is to unpack these global breakthroughs that really show this pivot happening. And it's not, one tech versus another. It's about needing both, driven by this almost unbelievable spike in electricity demand.
And if you look at the why, the data our research team put together, it's just staggering. AI training, running those complex models, hyperscale data centers, they're projected to drive something like 160% growth in global electricity demand just by 2030.
160%?
Think about that. That's like adding the entire power grid of several major countries just for computing.
It's almost hard to grasp the scale. And these places, data centers, AI, they don't just need power. They need perfect power, nonstop, high density. A tiny blip, a millisecond offline during AI training, that can cost millions.
Exactly. You just can't meet that kind of constant, rock-solid demand with intermittent sources alone. It won't work.
So that really sets the stage. The future energy mix isn't either anymore. It's got to be this smart, integrated blend. We absolutely need the green code. It's fast. The marginal costs are low. It's modular.
But we desperately need the hot core, too. For that baseload reliability, the density, the security. You need both sides of the coin.
Okay, so let's dive into this hot core pivot, starting with advanced fission. Because fission, it's giving us firm power right now. And this past week brought some huge news, some really strategic breakthroughs, especially from China, validating a whole new fuel cycle.
Yeah, what's really fascinating is this successful conversion of thorium-uranium fuel. It happened in the experimental thorium molten salt reactor, the TMSR LF1, out in Gansu province, China.
Thorium molten salt.
Okay. The Shanghai Institute of Applied Physics, they announced it's the world's first successful operational run of a thorium fuel cycle. This is a massive science and engineering step forward. They actually converted thorium-232, which you can't directly use for fission, into fissile uranium-233.
So they proved it can actually work in a real-world setting, breeding its own fuel.
Exactly. Proving that a sustainable breeding cycle can work outside the lab.
Now, our sources were making some pretty big claims about molten salt reactors, MSRs, being revolutionary. But, the U.S. looked at this stuff decades ago, back in the 60s, and then kind of shelved it. Can we really trust this is commercial now? What did they actually prove that gets past those old hurdles?
That's the million-dollar question, right? And yeah, there were historical challenges. A big one was corrosion. That hot molten salt is tough on materials over decades.
Right.
But this new generation, they're using better materials, improved metallurgy, sure. But more importantly, the whole operational model is different. See, normal reactors use solid fuel rods. You have to shut down, open the whole thing up, swap rods.
Right, the refueling outages.
Exactly. But MSRs, they use liquid fuel. The nuclear material is dissolved right into the molten salt coolant. It just circulates.
Okay, liquid fuel. So what's the big operational advantage then?
Continuous operation. You can basically refuel on the fly. You skim off the fission byproducts, add fresh fuel, all while it's running. That pushes your capacity factor way up, boosts efficiency compared to light water reactors that might be offline for weeks during refueling. Plus, safety, because the fuel is the coolant. It's the same liquid salt if there's ever a breach. The liquid just drains into passively cooled tanks below and solidifies. Turns into a solid block.
Ah, so it contains itself naturally.
Pretty much. You get inherent safety without needing those massive, super expensive pressurized containment domes you see on old reactors.
And the fuel itself? Thorium. You mentioned big strategic advantages there too.
Huge. First, you use the fuel much more completely. And crucially, for public perception, you generate way less long-lived radioactive waste compared to current reactors.
That's a big one.
Definitely. Second, geopolitics. Thorium is like 3 times more common than uranium in the Earth's crust. It's everywhere. That reduces the reliance on The handful of countries that control most uranium mining.
And I noticed something in the materials about the cooling for this reactor out in the Gobi Desert. No water needed. How significant is that?
Oh, that's absolutely critical for where you can build these things. Because the molten salt coolant runs at atmospheric pressure and holds a lot of heat, you can use air or other things to cool it. You don't need
Yeah.
tons and tons of water like traditional plants.
So you could put them in deserts, arid regions.
Exactly, like the Gobi, where the prototype is, or other drought-prone areas. It totally decouples advanced nuclear from water scarcity issues, which is a massive deal.
Mhm.
And China's not messing around. Their vision is clear. They're aiming for a 100-megawatt thermal demo project by 2035 based on this.
Wow.
It signals a real strategic jump. China's positioning itself as a leader in these Gen 4 reactor technologies.
Okay, so that definitely puts pressure on the West. Now, this hot core pivot isn't just MSRs in China. Globally, we're seeing this surge in small modular reactors, SMRs, and the regulations seem to be catching up.
That's the context, yeah. The NRC here in the U.S., they've moved to simplify licensing for advanced reactors. It shows the political will is starting to align. And we're seeing different deployment strategies popping up everywhere. SMRs are becoming this new export product.
And one of the really ambitious plans our research team flagged was in Indiana, Cameco, talking about the first closed fuel cycle nuclear park using lead bismuth-cooled SMRs.
Yeah, that's a big private bet. And the key promise there is the on-site fuel reprocessing.
Right. What does that actually mean, closing the fuel cycle on-site?
Well, right now, spent fuel is mostly treated just as waste. Reprocessing means you extract the valuable stuff left in it, the unused fissile material. Cameco claims that by recycling fuel right there at the plant, their system could eliminate something like 97% of the volume of that really long-lived high-level waste.
97%.
If they can pull that off, it fundamentally changes the conversation around nuclear waste. It addresses one of the biggest, longest-standing public concerns, reducing the long-term burden by almost 100-fold. That's huge.
And SMRs are also becoming tools for energy independence, right? Like that Canada-Belgium deal.
That partnership is really telling. It's about exporting tech. They're putting Canadian SMRs, the GE Hitachi BWRX-300 design, into Belgium to firm up their grid. Belgium had planned a phase-out, then reverse course. Now they see SMRs as a way to get energy security, less reliance on volatile global markets.
So SMRs are becoming a global commodity.
Absolutely. Backed by serious government money, too, like the 3 billion Canadian dollars Canada is putting into its program.
And here at home, big utilities are clearly hedging. Constellation Energy in Maryland, for example, they proposed adding 2 gigawatts of new advanced reactors at Calvert Cliffs. But they're bundling it, right, with batteries and even a gas plant that's supposed to be ready for hydrogen later.
Yeah, they're building an integrated system. Which brings us right to that economic debate we saw in the source materials. Are SMRs just niche, for remote mines or specific factories, or are they actually a grid-scale solution for the future?
Well, if they're inherently less efficient per unit than the massive gigawatt-scale reactors, which have huge economies of scale, isn't a $4 billion project like Fansolar potentially misallocating capital? Couldn't you build more existing, maybe cheaper capacity with that?
That's the core counter-argument, definitely. The high capital cost per megawatt is the main criticism. But the proponents argue the real benefit isn't just raw efficiency, it's modularity and speed.
How so?
Because SMRs are designed to be largely factory-built, shipped in modules. It cuts down construction risk, shortens timelines some hope under 3 years, and it makes them easier to finance, smaller chunks of capital.
Right, less upfront risk.
Exactly. It potentially opens up nuclear power to a whole new set of customers who need smaller, faster projects, like those tech companies needing that 247 dense power we talked about. It's a different kind of business model targeting that specific high-value power market.
Okay, so Fission is providing the immediate firm hot core. But our dedicated research team also saw major strides in the next generation stuff. Fusion and the advanced storage you absolutely need to knit the green code and hot core together.
Fusion, that's the ultimate hot core dream, isn't it? It offers that holy grail. 247 power, basically limitless fuel from seawater, deuterium, and lithium, and crucially, no long-lived radioactive waste like fission.
But the technical challenges are immense.
Monumental. Still, the physical infrastructure is starting to take shape. You can see it happening.
The research team pointed to a big milestone in China. At their best facility, that's the Burning Plasma Experimental Superconducting Tokamak, they just installed this 400-ton Dewar base. What exactly is a Dewar base in a fusion reactor, and why is 400 tons such a big deal?
Okay, so the dual base is essentially this huge, super high-performance vacuum chamber. It sits right at the bottom, the foundation of the tokamak. And this 400-ton piece, it's the biggest vacuum component China's ever made for fusion. It's structurally vital because it has to hold up the entire magnetic coil system, which weighs a staggering 6,500 tons.
Wow.
But the real engineering marvel is this base has to maintain an incredible vacuum and manage a temperature difference that spans almost 100 million degrees Celsius, right next to superconducting magnets running near absolute zero, all within meters. Getting that installed keeps them on track for operations around 2027.
So the global race for fusion is definitely heating up. Japan's new prime minister has even put fusion at the heart of their national strategy.
Yeah, that kind of top-level political backing is crucial for unlocking the capital needed. Japan's aiming for 100% energy self-sufficiency, and they want to demonstrate actual power generation sometime in the 2030s.
Ambitious.
Very. And backing that up, they recently had a successful test of a large-scale, high-temperature superconducting coil, an HTS coil.
Okay, HTS coil. Why is that a critical step? How is it different from the older superconducting coils?
Well, the challenge in fusion is creating and holding these incredibly strong magnetic fields to contain the superhot plasma. Traditional superconducting magnets, the low-temperature ones, need massive, complex, and really expensive cooling systems, usually involving liquid helium, which is scarce and costly.
Right.
HTS coils, though, can operate at significantly higher temperatures. Now, there's still freezing cold, but they don't need the liquid helium. You can use less complex, cheaper cooling. So this test, which replicated the magnetic conditions inside a commercial reactor, is a huge step towards making fusion reactors simpler and potentially much cheaper to build.
Okay, that makes sense. So we've got the firm generation side, but the green code part, the renewables, they only work if we solve intermittency, which brings us to storage. And our team found this really unexpected breakthrough using iron, like regular iron.
Yeah, it's a fantastic piece of material science. Basically, researchers figured out how to engineer iron so it can reversibly give up and take back 5 electrons per atom when the battery charges and discharges.
5 electrons. Why is that hard? What does iron normally do?
Usually, when metals like iron give up electrons in a battery, their structure gets unstable. They might lose 2, maybe 3 electrons, and then the material starts to fall apart. Getting it to reliably handle 5 electrons without degrading means you can store way more energy in the same amount of iron.
Ah, so it dramatically boosts the energy density.
Theoretically, yes.
Right.
Radically increases it. Makes iron batteries potentially competitive with chemistries that use much more expensive or problematic materials.
And sticking with iron, the strategic value there must be huge.
Oh, absolutely. Iron is, what, the 4th most common element in the Earth's crust? It's dirt cheap, it's everywhere. You completely sidestep the supply chain risks and ethical concerns around materials like cobalt, where, 70% comes from the DRC, or the price swings in nickel.
So it's a pathway to really massive scale grid storage that's affordable and secure.
Exactly. Ethical, low cost, globally available.
Okay, moving up the performance ladder. Solid-state batteries. They promise more safety, more density by getting rid of flammable liquid electrolytes. We saw 2 interesting developments there.
Yeah, first, Yonsei University developed a new fluoride-based solid electrolyte. The key thing here is it lets solid-state batteries operate safely above the 5-volt stability limit.
Why is 5 volts a barrier?
Because traditional liquid electrolytes in lithium-ion batteries start to break down, decompose, above maybe 4.3, 4.5 volts. Pushing past 5 volts safely while still letting ions move quickly allowed them to hit a record aerial capacity, this energy stored per unit area, of 35.3 milliamp hours per square centimeter. That's how you pack a ton of energy into a small, safe package.
Got it. And the second solid-state innovation used? Soybean protein. Seriously.
Sounds weird, right? But yet, Tsinghua University researchers use processed soybean protein as the electrolyte. It's non-toxic, biodegradable, sustainable. And it works. The protein forms this flexible but sturdy structure that conducts ions. And the crucial finding was that batteries using it were stable for 800 charge-discharge cycles, even at high temperatures up to 120 degrees Celsius. That's way beyond what normal liquid electrolytes can handle. Huge for safety and operating range.
Amazing. Okay, one more piece of the puzzle. To scale up all this stuff, hot core, green code storage, you need the raw materials for the batteries. Lithium's a big one, bottleneck.
Big time. Bottleneck, potentially. Which brings us to direct lithium extraction, or DLE. Lettuce Lee and C had some breakthrough pilot results down in Texas using nanotechnology filters. They were getting over 98% sustained lithium removal directly from brine.
Okay, DLE. What's the environmental advantage over, say, those huge evaporation ponds we see?
Massive difference. Those ponds use enormous amounts of land and water, especially in dry places like South America where a lot of lithium comes from. This nanofilter approach, it uses tiny amounts of power and water, and the physical footprint is way smaller. It's like comparing giant evaporation flats to targeted molecular fishing.
So it could unlock a lot more lithium much more sustainably.
That's the promise, making battery production way more scalable and much kinder to the environment.
These battery material and extraction breakthroughs are just so fundamental. They make the whole clean energy transition from massive hot core plants to distributed green code plus storage seem more feasible, more secure.
Yeah, they hit both the cost and the supply chain worries head on.
And speaking of scaling up, we want to scale up our audience here on Tomorrow Unveiled too. If you're finding this deep dive insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and maybe hit that new hype button on YouTube. It really helps us reach more viewers. And definitely turn on notifications so you don't miss what's next.
Absolutely. And if you're listening on Apple Podcasts, Spotify, or wherever you get your podcasts, leaving a rating and review for Tomorrow Unveiled would be fantastic. It genuinely helps new listeners discover the show and these critical insights we're discussing.
All right, so the tech breakthroughs are happening. But they're being met by this just incredible flood of political and financial support. It really confirms this pivot to the hot core is now a full-blown global race.
The momentum is undeniable. Our research team tracked projections. Global nuclear generation is expected to hit record highs in 2025. And the IEA thinks nuclear capacity could more than double by 2050 if all the current pledges get met, especially the ones driven by that AI demand we talked about.
And the biggest money story this week had to be that huge U.S. government deal, $80 billion strategic partnership with Westinghouse, Cameco, and Brookfield. That's not just a nudge, that's the government stepping in as a major market shaper.
It's squarely aimed at getting new reactors built, both the big AP1000s and the smaller AP300 SMRs. It's all about hitting that ambitious U.S. target, quadrupling nuclear capacity to 400 gigawatts by 2050.
And it's more than just a subsidy. It feels like a strategic move to rebuild a critical industry.
And our team flagged this really interesting detail about the public getting a stake. How does that work? The government gets a piece of the action. Yeah, it's a clever structure. The U.S. government will actually get a 20% stake in Westinghouse's future earnings, but only after a certain profit level is reached.
Okay.
It ensures taxpayer money potentially gets paid back, and it aligns the public interest directly with the long-term commercial success of this massive decarbonization effort. It frames nuclear almost like essential national infrastructure, like highways or ports.
And this isn't just a U.S. story. The momentum is international. Japan also committed huge amounts of money to support U.S. energy projects.
That's right. Japan pledged up to $332 billion overall for investments, with a big chunk up to $100 billion specifically earmarked for supporting U.S. energy infrastructure, including nuclear reactor construction.
For both the big ones and the SMRs.
Yeah, supporting both the AP1000s and the BWRX-300 SMRs. It highlights how interconnected this is. Japan is strategically helping expand the nuclear supply chain it needs, while also trying to regain its own position in the global nuclear export market.
Okay, money's flowing. But beyond cash, we need to talk regulations, especially fixing that fuel bottleneck for advanced reactors, HALEU.
High-assay, low-enriched uranium. It's the fuel many of these new designs need, like TerraPower's Natrium reactor. Normal reactors use low-enriched uranium, LEU, that's under 5% enriched U-235. HALEU is enriched higher, between 5% and 20%.
Why do they need that higher enrichment? And why is the supply such a strategic problem?
The higher enrichment lets you build much smaller reactor cores. That boosts power density and allows for really long operational cycles, sometimes 10 years or more, between refueling. Makes the economics of SMRs look much better.
Okay.
The problem, the vulnerability, was that until very, very recently, Russia was basically the only commercial supplier of HALEU in the world. So building a domestic HALEU supply chain became this urgent national security issue for the U.S. and its allies.
Which leads us to that Framatome and TerraPower news from this past week.
Exactly. They've moved past just demos. They actually completed a metallization production lineup in Washington State.
Yeah.
And they successfully produced these metallic uranium pucks.
Pucks.
Yeah. It's not the final fuel yet, but it's a critical, technically tricky intermediate step, tuning enriched uranium gas into the metal feedstock needed for these advanced fuels. It proves the U.S. can build this capacity domestically and significantly reduces that dependence on foreign supply.
That's a huge step. And the policy shift is hitting even the big international banks. The European Investment Bank, which used to avoid nuclear,
Yeah.
they're funding it now.
That's a massive U-turn. The EIB announced a €90 million loan for upgrades at Finland's Olkiluoto nuclear plant. It signals that these big multilateral development banks are finally reversing those decades-old bans on funding nuclear energy.
And why is that so important?
It unlocks potentially huge pools of capital for nuclear projects globally. It aligns the big financial institutions with the EU's own policy shift, which now recognizes nuclear as a valid low-carbon energy source.
Okay, let's connect this all back to the beginning. Why are governments suddenly making these enormous multi-billion-dollar bets now after decades of inertia on nuclear?
It comes back to that AI and data center demand pull. It gives them the clear, immediate, unavoidable economic reason. You've got Amazon, Google, Microsoft publicly saying they need nuclear power. Collectively, they're projecting needing over 15 gigawatts of new capacity.
15 gigawatts
Yeah.
just from those few companies.
It's enormous. That's nearly 15% of the entire current U.S. nuclear fleet, all driven by needing stable, carbon-free 247 power for the backbone of the digital age. The sheer power needs of AI are making the economic case for the hot core way faster than climate policy ever could.
Okay, so the momentum for the hot core, technically and financially, it seems overwhelming. But this pivot isn't simple. It involves really complex trade-offs, controversies. The sources our team found highlighted this fascinating case study in Los Angeles. It perfectly captures the policy dilemma of bridging the gap to a clean future.
Yeah, the LA Department of Water and Power, LADWP, they just approved this $800 million modernization of the Scattergood generating station. And it was a direct response to a problem they created themselves, in a way.
How so?
Their goal of 100% renewable energy, it created this big reliability gap. When the sun isn't shining or the wind isn't blowing, they still need power. So they absolutely had to have a dense, dispatchable thermal power source, basically, a hot core bridge technology.
But the sticking point, the controversy, is that the plant is labeled green hydrogen ready. Sounds great, sounds futuristic. But what does that actually mean for when it starts up in 2029? What did the research team find?
Well, READY is doing a lot of work there. It's aspirational. Technically, the plant is designed to start by burning a mix, 30% hydrogen, 70% natural gas. The goal is to eventually get to 100% green hydrogen.
Eventually.
But, and this is the crucial part, the utility openly admitted that the green hydrogen supply chain needed the huge infrastructure for making it, storing it, piping it. It currently does not exist.
Wow. So they're spending $800 million on a plant that relies on infrastructure that isn't built, isn't costed, isn't even proven at that scale yet. That seems like a massive gamble.
It's a huge risk. Critics call it fossil lock-in. You spend $800 million now, guaranteeing you build and run a brand new natural gas plant for potentially decades just to keep the lights on. The clean part, the green hydrogen, gets kicked down the road to some future uncertain review.
And if that hydrogen infrastructure doesn't show up on time or it's way too expensive.
That LA is locked into burning methane for decades longer, despite the huge investment.
And the trade-offs aren't just about carbon, right? This bridge plant might shift other kinds of pollution onto nearby communities.
That's the environmental justice angle, the pollution shifting argument. While the long-term goal is solving the global CO2 problem, critics point out that burning hydrogen, especially mixed with gas, can actually worsen local air quality. Hydrogen burns hotter. That can increase the formation of nidus pollutants, nitrogen oxides. They're toxic, bad for respiratory health, and power plants are often located near disadvantaged communities. So you might solve a climate problem globally while creating a toxic air problem locally.
And the water issue came up too.
Oh yeah. Making green hydrogen via electrolysis uses a lot of water. And this is California, a water-scarce state. So you have this unresolved water-energy nexus conflict. The $800 million solves an immediate reliability problem, but potentially creates local air quality issues and huge new water demands, all acknowledged, but basically deferred. It's a perfect snapshot of how messy the transition can be in practice.
It really highlights the challenges cities face, even with the best intentions. Okay, let's shift to the other big controversy that always comes up with the hot core. Nuclear waste, specifically those really long-lived radioactive elements.
Right. We need to talk about iodine-129, I-129. It's a tough one because its half-life is incredibly long, 15.7 million years, and biologically it acts like regular iodine, meaning it concentrates in the human thyroid gland.
15.7 million years. Okay. And the sources highlighted a stark difference in how the U.S. and France handle this specific waste.
A fundamental policy split. The U.S. approach is primarily isolation. The idea is deep geological disposal, bury the spent fuel way underground in stable rock formations, seal it up, and keep it isolated from the environment for, well, basically geological time. Strict limits on any release.
Okay, bury it deep. And France.
France takes a different path. Reprocessing and dilution. They routinely reprocess spent nuclear fuel to recover plutonium and uranium, but during that process, I-129 gets separated and is released in low concentrations in liquid effluents, usually into the English Channel. The idea is the vast ocean dilutes it to presumably safe levels.
Dilute and disperse versus concentrate and contain. So what did the analysis from the MIT research team find when comparing the long-term environmental results of these two strategies?
The findings were pretty striking, especially looking long-term. The French approach, reprocessing and dilution, basically releases about 90% of the I-129 into the biosphere now, today. It enters the global environment, the oceans, the iodine cycle.
Okay.
The U.S. strategy, isolation via deep disposal. It results in a tiny fraction of that escaping over even immense timescales. The calculation was that over 1 million years, the U.S. method releases something like 100 millionth, 300,000 of the amount that the French method releases almost immediately.
Wow. So dilution might lower the concentration locally right now, but isolation offers this massive multi-generational environmental benefit by keeping almost all of that incredibly long-lived radionuclide out of the global ecosystem for potentially millions of years.
That's exactly the implication. It really forces a shift in thinking about environmental responsibility from just managing a local issue today to making choices that have consequences on million-year timescales. It shows how nuclear technology, for all its challenges, is pushing us towards these really long-term stewardship strategies like deep isolation.
So, wrapping up this deep dive on Tomorrow Unveiled, looking at green code and hot core. It's clear we're not just seeing tech get better. We're seeing a real fundamental strategic shift, and it's being driven by raw demand. Let's just quickly recap the 3 big takeaways our dedicated research team confirmed.
Okay, first, technology is maturing fast. The key hot core tech, China's Thorium MSR, that domestic HALEU supply chain breakthrough, the next-gen fusion parts, those 5-electron iron batteries are moving decisively from the lab bench towards actual engineering and demonstration. It's getting real.
Second, demand drives policy. That relentless, non-negotiable power demand from AI, from data centers, from electrifying everything. It's forcing governments and investors to make huge financial and regulatory bets on high-density power. Policy isn't really leading anymore. It feels like it's scrambling to keep up with the demand curve.
And third, the hybrid necessity. The future grid clearly isn't an either-or between low-density green code and high-density hot core. It has to be a smart, integrated system. Nuclear and maybe fusion provide that bedrock, 247 firm power and amazing land efficiency. Solar and wind bring the cheap, fast, modular deployment, and advanced batteries bridge the gaps when renewables aren't producing.
Yeah. The optimal scenario our research team modeled for truly clean, abundant power looked something like nuclear and fusion handling maybe 40% of global electricity as the firm base, then maybe 45% from solar and wind, all balanced by a massive 15% contribution from grid-scale storage.
That integrated system seems like the only realistic path to get reliable, decarbonized power for everyone, especially now that we have this huge new energy consumer on the block, AI.
We really want to hear what you think. If you're on YouTube or your favorite podcast app, drop us a comment. Let us know your take on green code meeting hot core. Which high-density breakthrough are you most excited to see happen first? The Thorium MSR, those HDS fusion coils, the 5-electron battery. Tell us.
And maybe a final thought to leave you with. Building on those trade-offs we saw in LA and with the I-129 waste, the technical case for the hot core. It looks increasingly proven. The money's starting to flow. But the real key to unlocking full decarbonization now isn't just invention. It's execution. Meaning actually building out that massive, often still uncosted infrastructure like a reliable domestic HALEU supply or a working green hydrogen network, and maybe even harder, overcoming those deep social and political hurdles. Where do you site these facilities? How do you manage the waste convincingly? How do you achieve genuine public acceptance?
Those are the make-or-break challenges for the future we unveil. Thanks for joining us on Tomorrow Unveiled. We'll see you next week.